13.6, Equilibrium Calculations, Part 1. And on the worksheet, after this part, you ought to be able to do number 1, number 2, and number 4. 4, Part 1 only. You can do Part 2 if you want to on the other side of the paper, but let me try to fix this out. Now, I was looking at the problems, and now I made these problems or got them or compiled them some time back, and years ago. And now I know that there might be a better thing for me to give for one of those, but we'll just see. So the first part, I'm going to be showing you how to do the math for all equilibrium in this chapter. So like this chapter is only on gas equilibrium, but I'm going to show you how to do the math for part of what's called the acid-base equilibrium, and a little bit of what's called KSP equilibrium. Let me see if it'll do better like this. It's just moving her over. So I'm going to show you. I know it's a little bit weirder angle kind of at the side there. Oh boy. Let me see if it works like this. Let me just try to. I think I had the charging cable on it. I don't know. Here I am. Let's see if it works. This should be the way it works. There it is. Okay. All right. Now, here I go. So, I'm not going to do the first one yet. The first one is actually pretty easy, but I'm going to wait and show you that another day. But the first day, I'll focus on the gas equilibrium. So we'll probably spend more than one day doing some samples of these. We'll see. Or you might be able to know how. I'll have to look at it to see if I've done sufficient samples of all these. So the first thing we see on gas equilibrium B, it says this. 570 torr of methanol and 570 torr of hydrogen chloride, both these are gases, are added to an evacuated container at 393 Kelvin. So at that high temperature, they're both gases. In order to synthesize chloromethane. Calculate the equilibrium pressures of all the reactants and products. So I'll explain what this means as I kind of draw a diagram. Okay. So first we have the equation CH3OH plus HCl gives you, and we do the arrow, we do it this way when it's going to be equilibrium, CH3Cl and H2O. Now it says that Kp is 5.9. You know what? It says 10 to the third. I want to say that it was supposed to be 10 to the negative third. I don't have my... See, this is one thing bad where I don't have my notes, my original notes for this. But let me just see what's going to happen here. 10 to the third. It might work okay this way. You know what? I think it might. Oh wait, oh no, wait for. Oh, I'm gonna get confused here. I tell you what, as I do the problem, I'll work it out and I'll tell you. I'll be able to see it better. I'll try to think it through ahead of time. But okay, here we go. So I might change that number. I can't remember if this is the one where I'm supposed to change it. Well, but this data could be wrong for what we have here. Okay, so here we go. So what we'll do is, first thing you always need to do is write the K expression. And this one, they gave you pressures, so that tells us we're going to write Kp. So for this reaction, Kp is going to be, now these are all gases, right? Yeah, gas, 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 gas. That's important. Because if one of these were, like, if it said H2O, now this is H2O gas. If it had been H2O liquid, you would leave it off. You'd only put the gases. So the pressure of CH3Cl, all right, and it's to the first power, times the pressure of H2O, first power, over the pressure of CH3OH, also the first power, and the pressure of HCl gas, also the first power. All right, there's your K expression, okay? Now, and I know I wrote mine, I should have written it over here. I always like to write the equation like this. Watch what I'm going to do. I just wrote it down, but I wasn't too good about this. I always make my equation to the right of this. So CH3OH, HCl gives me CH3Cl. But you know, for you, this will be written on your paper when you get a worksheet or on the screen when you're doing a quiz or test. And so you can just copy it down this way. Write the Kp. Then write this next to it. Okay, and I'm going to show you why. Now, the next thing you're going to do is we're going to make something called an ice box. Ice box. I-C-E. Some people call it the rice box because that means reaction, but I won't, whatever. Okay, but ice, this means the initial amount of the substance, the change, and then the substance amount at equilibrium. The equilibrium position will be down here. So, I told you my floor is like a desk, and my desk is getting cluttered down here on the corner. Okay, so here we go. I'm going to need to stand there. Okay. All right, so here we go. Initially, CH3OH, you have, let me look at the paper, 570 torr. It says they put 570 torr of this. I won't put the unit. 570 of HCl. And that's all they put into an evacuated container. So they only put CH3OH. I mean, of course, you have millions of these molecules. And HCl, millions of these molecules. They're about to react. Nothing else. So that means I have zero. Initially, I have none of this and none of that. No pressure from high H2O gas. No pressure from CH3Cl gas. Only these two things. Okay. What is going to happen over time? Can you tell, and sometimes I ask this, will the system, well, I'll ask it on later questions, but will this system shift to the left, or is it at equilibrium, first of all? No, it's not at equilibrium, because if it were at equilibrium, you could not have anything with zero. Because look at this, the equilibrium constant has to mean at equilibrium, at the bottom, that'll be equilibrium. But at equilibrium, this number times this number divided by that number times that number should equal the equilibrium constant, Kp. So it cannot be at equilibrium. Will it shift to the right or to the left to get to equilibrium? And we know it's going to shift to the right. I mean, if you wanted to think about the little, I don't have my little board, do I? Oh, yeah, my little seesaw board. Then you'd say, well, right now, there are two people sitting on the seesaw here, and nothing's right there. So obviously, you got to shift weight material to the right. You got to turn those from zero up to a bigger number. So anyway, so what is the change going to be? Well, the change will always match the stoichiometry. So watch this, and this is not the best example. Yeah, I can see that even though I'm doing this problem now, I'm going to do another one in a minute with the stoich, but it'll be minus x. That'll be minus x. X will be the amount of pressure that decreases as it shifts over. So some of this goes away. Now, because they're both 1, 1, 1, 1 ratio, that's minus x, that'll be plus x, and that'll be plus x. So, at equilibrium, you have 570 minus x of this, 570 minus x of that, and you have x of this and x of that. Now, if you even want to make a chart, they call it an ice chart. You know, you can even do it this way if you really want to be good about it. If it helps you to see the numbers better. You don't have to. Then, you're ready to do the math. Now, for the math, we're going to come over here and we're going to put our Kp value. 5.9 10 to the third. I'm thinking that number might have been one of these were incorrect. I can remember, but I don't know which one. It'll pop up somewhere. For CH3Cl, now you're gonna plug in. Remember, these all mean at equilibrium. That's true. So equilibrium is down here. At equilibrium, my CH3Cl is 570 minus x. Okay, my H2O pressure is all. I'm sorry. No. X. CH3Cl is x. H2O is x. So you love how I make these errors, but I caught myself really quick there. Okay. CH3OH on the bottom is 570 minus x. I was just looking, and you know that's the whole thing about these. You know, sometimes, and you'll be doing these a lot. You'll be doing a lot of problems of this as you practice. And I'm going to tell you, sometimes you'll go real quick, and you're like, oh yeah. You might not even write this down. You try to do it by your brain. I had it written there, okay, and I think that's why it caught me so quick, because otherwise I'll think, oh, I put this times this over that times that. No, it's the other way around. So you know, I quickly got those. X at equilibrium, and at equilibrium that's 570 minus x, and that's 570 minus x. Oh, you know what? This does appear, it does appear that this one is okay. This one is all right. Now, this problem is a rare problem and one of the easier problems that you can see. Sometimes it pops up on the AP. I'm going to show you why. Because on this problem, notice the algebra here. 5.9 10 to the third is equal to x squared over 570 minus x squared. Sometimes this happens, and it's called a perfect, we'll call it a perfect square, equilibrium perfect square. And what that means is, all I got to do to solve for this, since that's squared, just take the square root of that side and the square root of that side, and you can solve for x. So the square root of 5.9 10 to the third is 76.8. Or actually just 2 sig figs, 77. 77 is equal to x squared, x over 570 minus x. Okay, well actually I want to put parentheses. So you can see that now, well maybe I will put parentheses. So now you're going to cross and multiply with that. So 77, I might run off the board here. So let me try and do it here. 77 times 570 is 43890. Is minus 77x equals x. Can you see that if I cross multiply these two things, 77 times 570 is 43890. Now with sig figs, that's really going to be, well, let's go on and put 44,000. Would that be better? 2 sig figs. 44000. Yeah, we'll do that. Because we have some subtraction and stuff coming up. Minus 77 times x equals just x. So now 4,400, 1,000, I'm sorry, equals, add that to that side, 78x. So then you divide both sides by 78. Am I still on the screen? Just barely. So 44,000 divided by 78 gives me 564. So x is 564. Now what that tells us is, at equilibrium, how bizarre this is, but at equilibrium, the question was, calculate the equilibrium pressure of all products and reactants. Okay, so the pressure of CH3Cl equals 564 because it equals x. The pressure of H2O, and some people like to put the answer right below this, equals 564 torr. These are all in torr. Now, isn't that amazing? Because look at that. 570 minus 564 will be this one. It's going to be almost none of this stuff. So 570 minus 564 equals 6 torr is the pressure of CH3OH and the pressure of H2O. You don't have to do that math twice. They'd know pressure of CH3OH equals that. Sometimes they'll say pressure of CH3OH equals 6 torr equals pressure of H2O. And that way you're kind of covered all the math. But it's okay to do that. If you just show the math at least one time on the paper, you don't have to do it again there. Okay, so wow, almost all of these are just a little bit. 6 torr, 6 torr of that, and then, one of those two, 6 torr, 6 torr, and these two are going to be 564, 564. But that makes sense because Kp is a really large number, so that would tell us the equilibrium lies to the right. One of these problems along the way, I have to fix that number because it was incorrect, but not on this problem. Okay, so that's the format, but that's not the best thing. That's not the best example yet. Okay, I'm about to do a better example right now, but that's kind of a simple one. If you ever get a perfect square. Now the thing is, most of the time you don't get a perfect square. So let's just say that on all the homework between now and this chapter and the next chapter, all the equilibrium you do, you're like never going to see a perfect square, but maybe like once or twice. So when the AP comes around, it might, if they put a perfect square, it might throw you off. You might do it the other way. And it's okay too, but hopefully you'll catch it. All right. Now, here is, I did example B. Oh, okay. Example D looks really good. All right, and this is KC. And E is also KC. is there any point of doing one or the other? I'm just trying to see. 2 moles in 1 liter. Oh, you know what? D looks better. I don't think there's even any reason for me to do E at all. And letter C, I skipped that one because I think D looks a little bit better. Oh, I know what I might do though. Okay. All right. So I'm going to be jumping around. I might not work all these examples out in the next few days, but for today's homework, you'll just do these problems. The ones that I told you already, that number 1, 2, and 4. You couldn't do it yet. I still need to I got to tell you the main problem. I wish I had done this first now, but letter D first. It says a 2-liter flask is filled with 0.400 moles of oxygen and 0.800 moles of carbon monoxide. Assume that the value of the equilibrium constant at the lab temp is this. Okay, and here it is. Carbon monoxide is changed into carbon dioxide thanks to oxygen. Okay? 2 CO2 there, right? Yeah. Okay, 2, 2, 2, 4, 4. Yeah. All right, that's your reaction. Now, what you're going to do, this one it says Kc. So that now we want to write down our Kc expression. And for this one, it'll be CO2. Oh, I can just see that on E, the only thing is we gave, well, it's okay. CO2 is going to be on the top. Don't forget you put brackets and you square it. And on the bottom you have CO squared times O2. That's going to be your K expression. CO2 squared, these are all gases. CO squared and then O squared. I'm sorry, O to the first power. You don't even have to put the 1 there, but sometimes I do just to make sure I didn't leave a number out. Now, okay, now for this one, this is good because it has a little bit of stoichiometry. A 2-liter flask is filled with 0.400 moles of oxygen. So what that means is your initial oxygen, and sometimes I put a little O, I'll put initial, let's write that. When they tell you something like this, think about this for a minute. Your initial oxygen is 0.400 in 2 liters. 0.400 moles in 2 liters. That means what? 0.200 molar. So, and it also says 0.800 moles of CO. Your CO initial, or just C, not CO2, CO, is going to be 0.800 over 2.00, which is 0.400 molar. So 0.400, 0.200. A lot of times on an AP question, they will tell you this. Imagine this for an AP question. Then what they'll do, I didn't do it, they'll just say part A, write the K expression. You did that. Part B, they'll say, what is the initial concentration of oxygen or carbon monoxide? They'll probably just ask you one of them. And then you say, okay, 0.800 over 2 is 0.400 molar. Okay? They don't usually ask you both, just one of them. Then they'll jump to the last question. So what I'm going to do is I'm going to go into the ice box. And what's my initial amount of oxygen? 0.200. Oxygen here, 0.200. What's my initial molarity of CO? It is 0.400. They didn't say anything about carbon dioxide, so that'll be 0 initially. Okay, now what I'm going to do is I'm going to get to equilibrium, it's going to have to shift, we know, to the right. Again, because there's nothing here. So it's going to have to, some of this is going to have to go away, that go away to make that. So the amount of this that goes away, watch carefully, it's not going to be minus x, but minus 2x. Your change always has to match the stoichiometry of the equation. Remember that. Minus 2x, oxygen will decrease minus x because it's 1, and this will increase plus 2x. So this is why I said maybe if I had done this problem first on the video, that then you could, some of you could jump ahead after this question. You could already jump ahead and do the homework without seeing another one. But anyway, but you know what? I might try and do a different problem. We'll see if I'm going to do another one or not on this video. So 0.400 minus 2x, 0.200 minus x, and then 2x. At equilibrium, that's what you have. This is a very important problem. Do not skip. Do not skip. Oh my goodness. Okay, do not skip the problem there. Okay. Yeah, if you want to keep it like that, then at the end you can put your answers down there. All right. So number one question was, will this system shift to the left or to the right? Well, I kind of already did that for you, but it'll shift right. We know that because there was nothing here. You got to shift material. That means that when it says shift right, that means that whatever these were initially, these are both going to have to go down to react to give something there. Because these three numbers, these will end up being numbers that have to make that constant true, or the expression true. Okay, so, all right. So the Kc value was given to you as 5 times 10 to the third. Maybe this is the one that's wrong. Or maybe not. All right, 5 times 10 to the third equals, and I'm going to put 0.200. Oh, no, I'm not going to put 0.200. I'm going to put 2x, so, CO2. Don't me get mixed up. Oh, and watch this. 2x goes on the top, CO2. But also, you have to square it. Wow, what an important thing. So in the balanced equation, that 2 has a big effect on the amount here. Because first of all, it has to be 2 times x, not just x. And secondly, it has to be squared. 2x squared equals, for CO at equilibrium, it's going to be 0.400 minus 2x, and all of that will be squared, times the oxygen is going to be just 0.200 minus x. Okay, wow. So there you have it. Good. Now, I'll know in a minute if that number needs to be switched. I'll figure that out. Okay, and all I'm going to do is make that. You'll see, I'm going to make an easy change on it to make it work out just for what we're doing here. Okay, the next step, I'm going to do a little bit of the algebra here. Well, just a little bit of algebra. I'm going to take this and square it, so that's going to be 4x squared over, I'm going to still keep this, 0.400 minus 2x and 0.200 minus x. Okay, now, I'm just going to tell you something to save a little time, to not torture you, but maybe one day, in college they will torture you, but I don't know if I'm going to torture you on this, because we have a lot to do and a lot of things going up, but you certainly could if you want to do this. If I were to multiply these out, you see what's going to happen? You know, FOIL, remember FOIL, first, outside, inside, last, did you learn it that way? Well, when you multiply this in algebra, and you have squared and some x's that aren't squared and some numbers that are like whole numbers there, you're going to end up getting an expression where you have to use the quadratic equation to solve it, okay? And that's a yucky thing. So a lot of equilibrium problems in real labs have to be solved with the quadratic equation. In college, you might get a teacher that requires you to do something with the quadratic equation to solve a problem. I'm going to let you know, you're going to hear more about that as I go forward. But we're allowed to avoid the quadratic equation by making an assumption. And what our assumption is, if we assume that the change, the amount that is subtracted, is so small that it doesn't greatly change these two, then we're allowed to ignore it. Actually, let me think about this for a minute. This has to be a -3. Let's just put it in as negative. I kept telling you about changing it. I believe that should be a negative value, not a positive. We're going to see what happens. I just going to jump in there and say it. Let that be a -3 and not a +3, okay? Because I believe, I told you, something was typed wrong, and it could have been that one. It might be the next page, or maybe both of them. But anyway. Okay, but we'll just let that be negative. Normally you would not ever do this on a problem, but I'm just doing it right now. Just saying I'm going to assume I made a typo error because I didn't work it out before the video here. But I've got it worked out somewhere, but it's at school under all these all these papers, I guess. But anyway, here we go. So what we're going to do is we're going to do this next step. When you get to the point where you realize, okay, I've simplified this. I'm going to probably get an expression that needs quadratic. Uh-oh, I got some technology issue here to deal with. All right. Then what you do is this: when you realize, hey, quadratic is on the way, and I'm going to write this. Assume x is negligible. Negligible means it is so small that it's not going to significantly affect the amounts that we have. And this will be the only problem I'm doing in this video today, the last one. So here we go. So assume x is negligible. Now, you can also do this. If you're seeing, instead of the equal sign, put, oh no, I'll keep that equal. So what you can do is, you're at 5 times 10, negative 3 is approximately equal. So you put the approximately sign, not that, equal to 4x squared over, and watch what I'm going to do, 0.400 times 0.200. What you're saying is the amount of this that changes is so small that we can ignore anything subtracted. We ignore the changes for these right down here. The minus 2x, we ignore the 2x. We ignore the x. Isn't that amazing? And now your algebra becomes a lot easier, of course. So I'm going to make it negative 3 to see if that works. 5 times 10 to the negative 3 times 0.400 times 0.200 equals 4 times 10 to the negative 4. I think I did the right thing. And again, let me tell you, never just change the KC value. It's just that on the paper I had it wrong, and I would have gotten a weird. It would have. Well, I don't want to. I'll tell you at the end perhaps why. But so 4 is 10 to the negative 4. 10 to the negative 4 equals 4x squared. Divide them both by 4. I'm going to run off the page. So 1 times 10 to the negative 4 will equal x squared. And now we get the square root of both sides. And so it's going to be 0.01. 0.0100 equals x. That's your answer. And that sounds like a good number. So this answer will be 0.400 minus 2 times 0.0100. So 2 times 0.0100 is 0.02. So that's going to be 0.380 molar. That's going to be your molarity of CO at equilibrium. For oxygen, it's going to be 0.200 minus 0.0100, which is 0.190 molar. And for this one, it's going to be 2 times 0.010, which is 200 molar. It's going to be a very small number. There are your 3 answers. Now, let me just mention this. The rule is that you can assume x is negligible anytime that the change is 5% or less than the original amount that you had. Okay, if it's 5% or less than the original amount that you had. I'll just check and see if that works out on mine. Yeah, it's exactly 5%. If I take 2 times this, x, the change is 0.0200. Divide by that, gives you 5. Yeah, so I knew I had to put that, I had that number wrong there. Well, if it's 6% or 7, then you're supposed to multiply this out and use a quadratic equation. However, AP has never required you to do the quadratic. And even if they gave a problem, and they did some years, that was greater than 5% change, then they gave it, but they still allowed you to use a quadratic. So you don't have to worry about that, okay? I'm standing in the way. So you don't have to worry about the quadratic, okay? Now, the bad thing is, how are you going to know in college? How will you know in college if you can use a quadratic or not? Well, you have to go through the entire problem, and at the end, you check it to see if 2 times that number, all right, in this case, divided by that is 5% or less, okay? Or it could be also this one, I guess, 0.10 times that. And they both end up being 5%, I think, just about. So, all right, and you're okay. So, that is all. So, work number 1, 2, and 4, part 1. And then, I'm either in class or in another video, I'm going to do some more calculations for you. I'll do another video, a part 2 of this, yeah, for sure. But I might try and show you a different one. Even the ones in the notes, I might not like them as much. I use these 2. I know I'm going to do letter A for you for sure, because that's actually the easiest one. And I skipped that one We'll save that one for when we do acid intro a little later on. All right, see you guys.